Okay, let's come to the new chapter, chapter 8. Now we are go into the subject that become more and more useful and practical. Okay, now this chapter we first introduce the concept we call transmission line theory. Okay, the transmission line theory. What is transmission line? Okay, transmission line. Let's take a look of this picture. Okay, take a look of this picture. Does that look familiar? Yes. So that basically is a very common PCB circuit board. Okay, we call printed circuit board. Or we call PCB, right? Okay, PCB board. So this is top view. This is top view. We see all the traces, right? And then for very simple transmission line on the PCB circuit board that looks like this. Okay, we have a printed metal. Okay, that is just a metal trace. Then with the ground is all, the ground must be realized by metal, right? So this is ground. Okay, this is ground. Then if we look at the side view, okay, we have a cross section. If we take a look at a cross section, what we see is this is a trace. Then the solid line, this is the electrical field. Okay, the dashed line is the magnetic field. Okay, so this is a very typical, even though you couldn't say it's a field, when you look at circuit board, there exists. You see, because we are talking about, today we are talking about high speed, high frequency. That's all in the domain of radio frequency and the microwave. And right now, even people looking at tens of gigahertz or even 100 gigahertz, that is called terahertz. Okay, so this is type of transmission line, right? Then people no longer interested in just using one trace or one transmission line. It's not, we couldn't say any circuit only contains one single trace, right? And then contains tens of thousand traces is not surprised. Okay, not surprised. If you look at the integrated circuit, okay, so contains hundreds of traces in a very small area. It's very common, right? So this is still, we are talking about single layer, okay. If this is single layer circuit, and in multiple time we are talking about a multi-layer circuit. The multi-layer circuit contains tens of layers. Okay, each layer you have a signal trace, you have a ground, signal trace, ground. So we stack up. So that compose high density packaging circuit. So here I just show one of the simple example. Okay, this is a 4 layer. Okay, packaging circuit. Okay, if your career in future relate to electronics, okay, you must deal with it. Okay, so when you look at trace, when you look at the trace, and then you know what that is. That is transmission line. Okay, not a wire. Okay, because we are all talking about high frequency, high speed. Let's look at a very typical problem. So if we have, say, input, okay, if we have input at one of the port, and we have output, okay, we have output, input, output. If you send a digital signal, say, if this is 1, this is 0, right? Ideally, the signal passing these trees takes time, right? Takes time. Then you have a certain time delay. You have a certain time delay. You have a certain time delay. This certain time delay, ideally the pulse, the 1 still 1, right? 0 still 0. This is ideal. But in reality, it never be like this, okay? Because we have corner return, right? We have go 1 layer down and 1 layer up, right? Because here we have many other circuits need to be wired, okay? Routing, we call routing to lay out different circuits, right? Because there are so many of them. Then as a result, your input signal looks like this is ideal. This is ideal. This is practice. This is practice. The practice, the input, this is the output. Then you see the waveform changed. The waveform completely changed, okay? But if you sample here, if you sample the pulse here, it may, the signal level may lower than your threshold value. You may treat it as 0, okay? Then if this is 0, 0, suppose the signal you send is 1, 0, right? A digital, right? Now you receive 0, 0, so the signal is distorted, right? We call this problem, we call signal integrity problem, okay? Sure, we have, as a human being, we are talking about to have a good integrity, right? Signal also need to have integrity. All this is happen on digital circuit, okay? So that is happen because of the transmission line, in fact, because of high frequency, in fact, okay? So we are talking about, we are dealing with electromagnetic coupling. We're talking about, right? We are talking about the electromagnetic coupling. And then those circuits also become small antennas, so they can radiate because you have a current flowing on it, okay? So you have a radiation effect, okay? Then we have a material loss because the PCB circuit board using FR4, that material that is kind of a fiberglass, it's lossy. Conductor also has a loss, okay? Have a finite conductivity, so you have a material loss. And then also we are talking about dispersion effect. So that is something is that property, for example, the impedance change with frequency, we call dispersion effect. All these phenomena we need to deal with. We need to keep in mind, okay? When we deal with the product or either design or even you just use it, okay? You need to know how to explain those phenomena like this, okay? Like this, right? So we have many type of transmission lines. I don't know how many, okay? And you can invent your own type of transmission line. If the transmission line has you invented has a very good characteristic, and the other existing transmission line don't have. You see, for example, very easy to make, very low loss in certain application, certain frequency, right? And then very cheap, low, you say cost effective, right? You see, for example, we have also another type of transmission line we call strip line. The strip line compared to microstrip line. Okay, compared to, this is a micro. Is, you see, we have two ground planes. Okay, this is a ground plane. This is also another ground plane. We have two ground planes. Okay, so the radiation effect become minimal. Okay, become minimal. So this is also a type of transmission. You see, the coaxial cable is very commonly seen, right? And then I guess your home cable TV, so you use coaxial cable, and this is a very old-fashioned transmission line using twin line. It's a very little application right now. You see, in the old time when you have a set of televisions, or you have external antenna, and that antenna connect to the TV, you use twin line. You see, the reason is that type of transmission line is very easy to make it, and also the performance is pretty good, you see, in the low frequency. But when frequency is high, people don't use that anymore. Okay, and also we can have a two parallel plate conductor. If we have two conductors in parallel, and the electrical field can exist between two conducting plates, okay, then they can propagate like a plane wave, okay, like a plane wave. We will use this as an example in our discussion. Okay. And also, this is a microwave circuit. Okay, so microwave circuit, you have different functions. Let's say, for example, this is called coupler. Okay, then you have kind of amplifier, the power divider, and so on, right, to perform certain functions. So this is also this type of circuit, and many of them have been replaced by integrate microwave circuit. Okay, those are just the application, right? And then we need to understand what is the theory behind, right, to help us in future how to design such a circuit. Okay, how to design such a circuit. Okay, I just skip this, so I already spent too much time. Those just show you what the electrical field looks like, you see, inside the coaxial line. And the electrical field and magnetic field, also the field down a microchip line. Okay, now let's back to our real business. Okay, we have two chapters dedicated to transmission line. Okay, I emphasize transmission line. Okay, maybe this is first time for you to hear about this word, transmission line. Okay, transmission line is very different from what we call electrical circuit. Okay, so microwave circuit or our radio frequency circuit is very different from what we learned in basic circuit theory. Basic circuit theory is assume the frequency is so low, okay, so the circuit size does not matter, okay, but transmission line, everything, every size is counted, okay, so the dimension of transmission line really determine the performance of the circuit. Okay, so we will see soon. Okay, so we have two chapters deal with transmission line. This chapter we deal with transmission line and its application for digital electronics. And another chapter we deal with transmission line. We talk about transmission line for communications. Okay, for communication. Now we can see the transmission line in this discussion we treat it as uniform plane wave, but not propagating in free space. It propagates down a two parallel plane, okay? And we consider is perfect conductors, okay? We consider a perfect conductor. That means no loss, okay? Then we treat it as, we have two. So I should say this is infinitely, so it's infinitely long, okay? But however, the electrical field can exist, okay? The magnetic field also exists down. This is H, this is E, okay? This is E. Then the behavior of electromagnetic wave down such transmission line is the same as plane wave we have learned. So we can discuss this material very quickly, okay? But important things for transmission line is we need to discuss is called the distributed parameter equivalent circuit, okay? So once we understand the equivalent circuit, then that really help us to do the analysis, and also don't have to look at it from field point of view, but we can treat it as a circuit, okay, to make things simple. Okay, so this is what we are going to do. Right. And also, actually, the second part of today, this is what I plan, is we are also going to discuss, okay, we are also going to discuss time domain analysis. Let's say if we launch a pulse, okay, down a certain transmission line with a different termination or different circuit between, okay, what is the response in time domain? What we can predict from it. And I think we already filled some of the flavor by doing the lab experiment, okay? But we are going to discuss what is the theory behind, okay? So very soon we'll see for transmission line, for transmission line, what we are going to learn, what we are going to describe it, we using circuit concept. Using circuit concept is always, we use circuit concept of the conductance, capacitance, and inductance. Very importantly, we talk about per unit length. Okay, so we'll come to that point soon. All right, okay. When we discuss a plane wave, we have a very important concept we call intrinsic impedance, right? For intrinsic impedance, what that means, for intrinsic impedance is intrinsic mean for a medium, right? So let's say for medium, if we know the permittivity, okay, we know the permittivity, we know the permeability, the intrinsic impedance become equal to this, right? So for free space, is 120 pi, okay? So approximately equal to. So that is the intrinsic impedance that only determined by the media, right? Only determined by permittivity and the permeability, okay? Only determined, has nothing to do with your antenna, right? Okay. Same as transmission line. For transmission line, we also have intrinsic impedance. Those intrinsic impedance only determined by the geometry of the transmission line. You see, for example, for parallel plate transmission line, we know its intrinsic impedance. Let's see, for coaxial capacitance inductance. Oh, I didn't give intrinsic impedance. Okay. Okay. For intrinsic impedance, we also have intrinsic impedance for transmission lines, but we use a different notation. We use Z sub 0. We were going to use Z sub 0, okay? And this can be justified. That equal to R over C. The L is inductance per unit length. Okay, then C is capacitance per unit length. Okay, so those values, those L and C, we're not talking about a lossy case, so we don't discuss the conductance, okay? But that also can be obtained mathematically. For those parameters, can be determined by electromagnetic analysis, okay? So I suppose we should learn something in the physics, in engineering physics, but I don't know, have you got a chance to learn that or not? Well, but that can be obtained, okay? That can be obtained. For example, you say for capacitance per unit length, for different transmission line, for parallel plate, for coaxial cable, you see, we can find only determined by the dimensional parameters such as A and B, right? We assume we can find all these capacitance inductance values for different type of transmission, right? Okay, and also you can find from textbook. Okay, so we don't discuss how they obtain, but we will discuss the behavior. Okay, once those intrinsic impedance or capacitor inductance is known. Okay, now let's do an analysis. We assume we have a parallel plate. We have a parallel plate transmission line. Okay, the parallel plate transmission line, we have, this is a conductor, we have a conductor, we have a conductor. Okay, we have a conductor. Then that suppose we have finite width. Okay, we have a finite width. This width is wide enough that doesn't affect the field distribution. Okay, right. Then the field propagate along that direction. Okay, along that direction. Then such conducting plate, I also has a certain okay. So I only cutting from the middle, cutting the line, we can see the electric field and the magnetic field. Okay. Now, okay. Now we can such conducting plate support electrical field polarized in X direction. Okay. So electrical field, so this is X direction. Okay, this is X direction, this is Z direction. X, this is a Y, this is Y direction. Okay, so such conducting plate we can support electromagnetic field such that only EX exists and HY exists. Then you may say, hey, this looks very similar to what we assume for plane wave, right? Yes, you're right. So we use the same coordinate and the same field component, just make consistent to the symbol we use, okay, or the component we already use in discussion of plane wave, okay, to make our discussion continuous. But not necessarily I have to call it X coordinate or Y coordinate. This is completely for convenience, right? But nevertheless, the electrical field, we know the electrical field on the conductor tangential component is 0, right? And then only normal component. So therefore, that's why you say if we have a two conducting plate, the electrical field must be perpendicular to the conductor and also perpendicular to another conductor, right? So that's why you see we see two parallel plates, conducting plate, can support vertical electrical field. And similarly, if you have a vertical electrical field, you can support tangential magnetic field, because tangential magnetic field on the conducting plate not equal to 0. And also, we know the charge distribution. If you have a vertical normal component of electrical field, it's a normal component, okay, equal to charge density. Okay, so that means on the charge, on the conducting plate, we have positive charge on one side, we have negative charge on another side. Okay, so this is how we obtain the charge. We can also obtain the current. Because this is what we learned in boundary condition is the tangential magnetic field. So N is the normal direction. N is where I show my N direction. If this is a N direction, this is N direction. Okay, so N cross magnetic field. If magnetic field is in Y direction, then if I look at the lower plane, N direction cross Y right? That direction is, so that basically X cross Y. So that electrical field, the electrical field is propagating, in that direction, okay? The propagating in that direction, okay? So if this is a when you locate in at X equal to 0, that means at the lower conducting plane. But if you stand on the upper conducting plane, the normal direction is in minus X direction, right? And then if the magnetic field on the upper plate is change the sign, changes the sign, okay? So that means the magnetic field, let me draw magnetic field. The magnetic field go like this. Okay, the magnetic field that support the magnetic field must be in a loop. Okay, so you have on lower plate is in Y direction and the upper plate in minus Y direction. So N cross minus Y direction, the current, sorry. No. Sorry. Magnetic field. Okay. Sorry. Okay, I take it back. The magnetic field still in the same direction. Okay. So in this case, the magnetic field. The magnetic field inside this plate is not changed. Okay. So inside this plate is not changed. So what we have is at the lower, in the lower plate, this is N direction. Upper plate, the N direction is opposite, right? So therefore, we have a current in the lower plate is in that direction. In the upper plate, is in the opposite direction. Okay, so that cape, that makes sense, you see, because the electromagnetic field down the parallel plate, okay, support current of one conductor flowing in one direction, and then also the upper plate provide the path for returning current, okay? The current go in and come back. So therefore, it's two different plates, okay? For two different up and the lower plates, the current in opposite direction, okay, in opposite direction. Now let's say we have electrical field in this direction. Then let's define the integration of this electrical field. Okay, so this is now we define the X. Now we define X. Okay, so upside and down. So now, if we have electrical field, the electrical field, let's do a line integration along electrical field at a certain Z position and at a certain time instance. Okay, then because the electrical field we assume between the two conducting plates is a constant, is independent to X. It's not a function of X. Okay, then this integration is simply just multiplication of the total field times D. Okay, so this is how we define voltage, because the voltage we can define is the line integration of electrical field. But now let's only do the integration along this path, okay, along this path. Then we can try to find the current, the total current, the total current where, so we assume this, the line width is W, okay, we assume the line width is W. Then we know the current density. This is current density. Okay, the current density G we know is N cross H. Okay, N cross H. On the boundary, what boundary? Let's assume it at the boundary at x equal to 0. Okay, at x equal to 0. So on this surface, so we have a current GS. Okay, GS. Then this is only the current density along Y. Then we collect all this density, okay, by add them up together, we form integration. Then we find the total current, okay, the total current, because this magnetic field is not a function of Y, okay, so this integration is just simply magnetic field multiplied by a width of this strip. By the way, so this transmission line is infinitely long, right? This infinitely long. This is infinitely long. Okay, so we know the total current. We know the total current. I write the big current. Okay. Okay. We also have a voltage. We have a voltage. Okay, by integration of electrical field. Then let's say if we want to calculate the power, the total power goes through, okay, carried down the transmission line, then we know the Poynting vector, right? Because right now we're not talking about time harmonic. We are talking about the general field which is a function of time. So the Poynting vector tells us the power density is E cross H. This is what we call power. Okay, Poynting vector. Okay, Poynting vector. Then we do the integration across this. This is S. Okay, this is S. Okay, let's do the integration of total power crossing. Okay, then we know the electrical field symbolically, right? E cross H, basically X. E is in X component, H is in Y component. So E cross H is EX multiplied by HY. And then the direction is in Z direction. And but the DS is differential area, right? So that is in that direction, DS, all right? So this is dz dot product. So dz dot, I'm sorry. Oh, sorry. Equal to 1, right? Equal to 1. So this is also we found E related to voltage and H related to current, okay? Then you substitute in, you say, hey, this is exactly what we learned in circuit theory, right? The total power carried, you see, in a conducting wire, okay, that equal to voltage multiplied by current. Okay, so this is the voltage and current. Now, let's recall the Maxwell equations. Okay, everything we deal with is related to is governed by Maxwell equations. Okay, so because it's governed by Maxwell equations, also we know we only have Ex component, Hy component. Okay, the field does not change with X, does not change with Y, right? Does not change with Y. Under all this condition, these conditions we use for plane wave, right? The condition for plane wave. So exactly the same equation that should be satisfied. Okay, so we don't repeat. Then we should say, under this condition, from Maxwell equations, we can write this. Okay, but in order to find the analogy between the field and the voltage variable, specifically voltage and current, okay, compared to the field quantity and the circuit quantity, okay, let's find a relation. Okay, let's find a relation. So we substitute the Ex by voltage divided by D, right? And the magnetic field is the current divided by the width. Okay, right? So we substitute them into this also concept, the conductivity equal to 0. Okay, in the medium, that means lossless. Okay, so we have another set of equation is this. Or you see, if we multiply this D on this side, right? So this exactly equal to this. Now we can see, compared to, take a look of this. Take a look of this equation. Take a look of this equation. What does that mean? That means exactly, if we recall the definition, of what is inductance? The voltage and the current related to inductance. What is a relation? Relation is, this is how we define inductance, right? And how we define capacitance? How we define the capacitance? The capacitance is the current goes through the capacitance. Okay, goes through the capacitance is, all right? Okay, so if you compare this basic circuit theory, okay, compared to what we have derived here, okay, then what I can say is, this is a voltage unit length. Do you think so? You see, because this dz is normalized, right? This is per unit length. So that means how large voltage you divide by the total length, right? So that means it's a normalized voltage. This is normalized current. Okay, this is normalized current, right? Then under this circumstance, I can say this is an inductance per unit length, okay, for parallel plate transmission line. And this is capacitance per unit length, right? Okay, don't worry about this negative sign. The negative sign is just the reference direction of voltage or current, okay? But the quantitatively, this is what I said, okay? The quantitatively, right? So in another word, okay, we have a very famous transmission line equations. Okay, we call transmission line equation. Okay, so that means everything, the voltage and the current down a transmission line is governed by this set of equation. This is also okay in circuit form. Circuit form of Maxwell equations. Okay. Even although we derived this relation using parallel plate type of transmission line. This equation is also true for any other type of transmission line, as long as you see this voltage, as long as these conditions is satisfied. Okay, this condition is satisfied. Then let me. Okay, let's take a break for 10 minutes. We resume at 10:30. All right. Okay, let's come back. So when you say this, both voltage and the current satisfies the Maxwell equation, so then you should show that does that also satisfy the wave equations? Yeah, yes, of course. You see, if you have, say, equation 1 and equation 2, okay, then you take the partial z on equation 1, okay, so that you have right, and then if you take the partial derivative with time on equation 2, right? Okay, so if you substitute this into this, okay, then what you have is you eliminate current, right? Then what equation we have is this is exactly the wave equation, right? This is wave equation. So you can derive the same wave equation, the same equation for current I. So that means down the transmission line, the voltage and the current must satisfy the wave equation. This is not true for ordinary circuit, okay, for ordinary circuit. So this is a very special property for voltage and current down the transmission line. And also we can see for given transmission line, for a to represent a very short section of transmission line, we can use its circuit equivalent. Okay, the circuit equivalent for a very short transmission line. Okay, we represent by a very short transmission line of length delta Z. Okay, delta Z. So this circuit is composed by series inductance, shunt capacitance, series inductance, shunt capacitance, and so on. Okay, so once you know the unit inductance and the unit capacitance, then you can compose by this transmission. So then you can say the unit length inductance and capacitance is very important, right? So that determines what the circuit model is. Okay, to justify this circuit model is not difficult. Okay, it's not difficult because if you start from this equation we already derived, right? We can find the differential form, okay, to represent this derivativity, right? Okay, by finite difference. Okay, we use finite difference approximation, okay, to represent this derivativity with respect to Z, and also we can have similar equation for the current, okay, for the current. Then this equation, what I represent is, on left hand side, this is the voltage at Z, at the location of Z plus delta Z, right? And this is this voltage. And we have this voltage by this, right? Okay, by this. So this voltage minus voltage is equal to voltage across this inductance. Okay, across this inductance. And then this is total inductance. Okay, this exactly by follow the definition of inductance. Okay, pay attention to the direction of current. In this case, the direction of current is not in the ordinary circuit model. Ordinary circuit model is the current is go into this. Okay, this is a circuit theory. Okay, but in microwaves, in RF transmission line theory, the current is going out of the plus sign, not go into the plus sign. So that's why you see, because we have minus sign here. If we don't have this minus sign, then we have a trouble to satisfy the wave equation. Okay. Similarly, the second equation to explain the capacitance. Okay, so once we combine these two, we can form this circuit model. Okay, We can follow this circuit model. So similarly, we can explain the power. We can explain the power stored in capacitance and stored in inductance. Okay, so that is same as our circuit theory. So therefore, we can have a comparison. Okay, compare to the field quantity and the circuit quantity. Okay, so electrical field corresponds to voltage, magnetic field corresponds to current, and the permeability corresponds to inductance, and the permittivity corresponds to capacitance. Okay, right. And also, we said, and also you see, we have a set of Maxwell equations, and then that corresponds to circuit theory equation, transmission line equation. Okay, transmission line equation 2, right? Then we already justified both voltage and the current satisfies the wave equation. Okay, satisfies the wave equation. And then we also know the wave equation. This term basically L times C equal to the velocity square. Okay, this velocity square. So therefore, we know the wave velocity is this, the wave velocity. And then if you find, but we didn't, we can easily prove is if the voltage divided by current, okay, if voltage divided by current, that equal to the wave impedance, okay. You see, because we know the voltage, we know the current, then in terms of circuit theory, right? So we can easily find V divided by current, we define as intrinsic impedance, okay? Then we know the solution for the wave equations. The solution for wave equations is we have two functions. One describes the wave propagate in positive z direction, and one function describes the wave propagating in negative z direction. Okay, negative z direction. Then the ratio between the wave in one propagating in one direction is intrinsic wave impedance. Right. So now we know the solution for. Now we know the solution for. Okay, so any questions? Yeah, you can type your questions, fine. You know, you see, so basically to find you mean this slide? Sorry, what's your question? Okay, so you see, because we have this relation, right? I can easily leave it to you. You can find V divided by I. Okay, you can easily find V divided by I. Then what that means is V divided by I is Ex times D divided by Hy times W, right? Okay, so this equal to wave intrinsic impedance times D times W, okay? Then also you can find epsilon and mu related to the capacitance and the inductance, okay? So then you can find that equal to the L over C, okay? You can very easily to justify. So we don't call this code in, we don't use the eta anymore, we use characteristic impedance for transmission line. Well, this is almost international and universal convention. Okay, we use this sub-zero to describe characteristic impedance of transmission line. That is determined by the inductance and capacitance per unit length. Okay, so now let's move to okay, now let's carry on. Okay, now let's carry on. We know the voltage and the current. We know the voltage and the current follow this relation, right? Because voltage and current satisfy the wave equation. So now we know the solutions. Okay, so the solution form, but we don't know exactly what that is. Okay, so we use this symbol to represent voltage propagating in positive z direction. Then we use this symbol for the wave propagating in minus z direction. Okay, so since we know the relation between this and this equal to characteristic impedance, and this and this, the voltage and current in minus z direction equal to this. Okay, so equal to this. This is easy to justify from the equation we already had. Okay, right? Then we can find the total voltage. Okay, the total voltage is two traveling waves. Okay, two traveling waves superposed together. Okay, concisely. Okay, concisely, this is this. Okay, and to find this, we use these relations. Those are very basic concepts. Okay, or you can say the first principle. I don't encourage you to remember this. This is the first principle. This is by heart. Okay, this is by heart. It's not remember. This is the definition. Okay, this is definition. So if you ask, say, I have to remember what is Ohm's law. Sorry. Okay, this is not encouraged. Okay. right? Okay. Now we can find the total power carried by the signal moving toward that direction, that is voltage multiplied by current. Okay. Then the power carried by the signal, the voltage and the current propagating in minus that direction, okay, in minus that direction, that determined by the voltage magnitude of V minus, okay, V minus. So those are just a definition. Okay, so I like to see a few more words about final exam. Okay, and some students write me say, can we still have this information sheet and that make our life easier, right? So we not that much stressful. I have different opinion. You see, think about if we take a class, take a lesson without exam, what do you expect? Definitely, you have no any stress. Okay, stress is zero. Okay, what do we learn? What do we learn? Next to zero. Okay, next to zero. So stress is a good thing. Okay, stress is a good thing that everybody needs to have stress. Okay, so you ask me, do I have stress? Of course I have stress. Okay, if you go to a workplace, have no stress, I don't think you can find that kind of job. Okay, so having stress is a good thing. Okay, but how to relieve the stress? So that depends on how you learn. Okay, how you learn the subject. Some student is very good to relieve the stress because they know how to derive all these formulas, okay, using the first principle. All the equations we talk about, we start from plane wave, right? From plane wave expression, from what is the basic boundary condition we need to satisfy, okay? We can derive them less than 1 or 2 minutes, okay? So to find what is the reflection coefficient, what is the relation between voltage and current, and between electric field and the magnetic field, okay? So that all can be derived, right? So at the end, okay, we have no information sheet allowed in final exam, okay? So when you do a revision, when you do assignment, okay, use the first principle to solve problem, and then at the end you will say you don't need to remember anything, okay? Everything is already in heart. Okay. And if you ask me how to cope with the final exam, my advice is understand every slide in my note, do every problems in assignment by yourself. You understand every assignment by yourself. Okay, you won't have any question. Okay, you won't have any problem in final exam. So as simple as this. Do every problem by yourself. Okay, and understand it. Okay, that is my advice. So I hope I answered the question sent by email. Okay. Now we are talking about very interesting problem. Okay. is we have a transmission line. Okay, the transmission line with the length we have a transmission line with a length L. Okay, then we have intrinsic impedance Z sub 0, and also we have a speed of v. Okay, now the situation is this. The situation is this. I have a load, resistive load. So this is a resistor. Okay, very simple load, resistor. I also have a source resistance. I have a source resistance, and I have a battery with constant voltage. Okay, so this overall form a source. So any source you have, you can be composed by ideal voltage and internal source resistance. Right. Now I have a switch S. The switch turned on at time equal to 0. Okay, at time equal to 0. It turned on. The problem is, what is the voltage waveform? Waveform. Voltage waveform down the transmission line. Okay. Or if we down the transmission line, that means at every location of transmission, what is voltage form? So of course, the voltage form must be a function of time and a function of location. So if this is Z, right, function of location. Do you agree? So at the beginning, at time equal to 0, at time equal to 0, at the beginning, when the switch is on, okay, then you can imagine the voltage has no time to travel yet. Okay, so what the voltage can say is infinitely long, because the voltage hasn't reached to this end and find, oh, the terminal, the termination is another resistance, not Z sub 0. Okay, then at the beginning, the voltage doesn't know what happened down the transmission line. Then what you can say is, oh, this transmission line is infinitely long. Okay, so it's infinitely long, and what you can say is only the intrinsic impedance of the transmission line. So this circuit I can represent by the source impedance loaded by characteristic impedance, right? So the voltage across the transmission line is just a voltage divider, right? The voltage divider. So this is the magnitude of the voltage going to be traveled toward terminal, okay, toward terminal, right? Then what is the current? The current at t equal to 0 is what we have. The current is what we have, the voltage we have across the load, okay, this divided by this, right? So this is the current. This is current at initial voltage and the initial current. Okay. But voltage and current change with time, right? This change with time. The current also change with time. Also change with time. Then, so with time goes, okay. Time, how much time? Okay. When the time less than total length divided by the speed, that means the wave hasn't reached to the end yet. Okay, hasn't reached to the end yet. So at every point down the transmission line, okay, every point down the transmission line still unchanged, right? Still unchanged until this time happen. When this time happen, the voltage reach to the end. The voltage reach to the end. Then what will happen? Okay, what will happen? So when the voltage reach to the end, at one instant, the voltage equal to 1 plus. Okay, 1 plus. What is the 1 plus? The voltage of 1 plus is V0 times this, right? Times this. But this voltage is contradictory to what? To the voltage divided by the load. If you use Ohm's, if you just simply use Ohm's law, the current, so the current and the voltage is not as simple as this voltage and divided by R load equal to the current plus. Definitely not. Okay, definitely not. Okay. The reason is when the voltage hit on the terminal, okay, this R load is not necessarily equal to the characteristic impedance. Then because the voltage right now is a wave, that will happen is we induce a reflection of this voltage. So the total voltage across the terminal will be equal to the incident voltage plus reflected voltage. Okay, plus reflected voltage. So that is the total voltage. Okay, the same as the current. The current, okay, we also have the current in toward positive z direction and the current reflected toward the source, So therefore, the Ohm's law that's satisfied is by the total voltage and the total current. Okay, because voltage and current are a wave right now. Okay, so that still satisfies Ohm's law. Okay, the total voltage and the total current satisfies Ohm's law. All right. So according to this is the boundary condition we must satisfy. Okay, the boundary condition talking about the circuit is a terminal. That is the boundary, and is the boundary. Okay, and don't forget, both voltage, traveling voltage, satisfy this relation. This is the first principle. Okay, we substitute them into this okay. So we substitute this basic definition into it, okay, into it. Then we can find, we replace the current by voltage. We replace the current, no matter is a positive current and a negative current, we substitute them into this necessary condition we have to satisfy, okay? Then we can find the reflective voltage related to the incident voltage by a reflection coefficient. This is a reflection coefficient, okay? This reflection coefficient, do you recall what that is? This is exactly the same as we obtained for plane wave, right? In plane wave, we have two media. This media, we have intrinsic wave impedance determined by this, right? We have intrinsic impedance in medium 2 or in medium 1 determined by this. Okay. Now we are coming to the circuit, to transmission line circuit. Okay. Then this is the load. When we look at this reflection coefficient, this is the load. Right? This is load impedance. So gamma 2, eta 2 is a load, right? Eta 2 is a load. Now in the circuit, okay, the load minus itself divided by load plus itself. This is reflection coefficient, okay, reflection. So the same as plane wave, the same as plane wave. So that is the reflection coefficient for voltage, or which is the same as for electrical field. But if you like to handle the current, then if you like to define, let's say for voltage, if you really love to define a reflection coefficient for current, that's fine, okay, that's fine. But that is simply related to reflection coefficient for voltage by minus sign, okay, by minus 1, okay, by minus 1. So by the same token, we can also determine the reflection coefficient at source. Okay, just now we have load, right? So now let's look at the source. So when you look at the source, you look into this, okay? You look into this, and the short circuit, the voltage source, short circuit voltage source, what you say is RG minus the reflection coefficient for voltage at the load. Okay, so the reflection coefficient of voltage at, oh sorry, this is source. At the load is okay, which is equal to minus the current reflection coefficient at the source. Okay, the minus the voltage, the the current. Okay, right. The reason we talk about reflection coefficient source is the wave you expect when it first hit on, when the first hit on the load will reflect, right? Okay, let's look at this picture. Then what we expect, the wave travel to this direction, return, and the reflection, and the reflection, multiple infinite number of reflections back and forth. So we need to look at what is the reflection coefficient on this hand and the reflection coefficient on this side. Okay, this is source, this is load. Okay, if you look at the voltage, then we look at voltage reflection coefficient. If you're looking at the current, then we use the current reflection coefficient. That's why we need to deal with full, right? But the relation is simple, right? We always take a voltage reflection coefficient as a reference, and always the load minus itself and divide by load plus itself. Okay. Right. So if you get confused, hey, should I have minus 8 at nominator? Should I have this? Okay, I divide it. Okay, should I have this or have this? Remember, you can have 0 reflection. So that means no reflection. So if in this case, you don't have 0 reflection, right? You have infinite number, infinite large reflection. This is physically not exist. The reflection coefficient, because reflection coefficient always less or equal to 0. Okay, right? So when you get confused, forget about this. Okay, this never exists. Okay, so only this that satisfies this relation. Okay, then let's talk about why reflection coefficient less or magnitude less or equal than 1 is we have 3 special cases. Okay, one is the load is 0. Okay, the load is 0. One load is 0. What that means is short circuit. Okay, short circuited. Okay, the voltage is equal to 0, right? Short circuit. In this case, your load equal to 1. Oh, sorry, equal to 0. Okay, load equal to 0. When load equal to 0, you have reflection coefficient, voltage reflection coefficient equal to -1, right? Another special case is when the load equal to infinity or infinitely large, that means the current, you see, the load equal to the voltage divided by current, right? So when this goes to infinity, that means the current goes to 0, right? So that means it's an open circuit, okay? I connect nothing, open circuit. The current is 0, no place to go, okay? The current is 0. This is another special case. In this case, infinity divided by infinity equal to 1. Okay, so this is the second special case, right? The third special case is your load equal to characteristic impedance. In this case, reflection coefficient equal to 0, no reflection. Okay, all the signal or energy absorbed by the load. Okay, or if any case between them, where reflection coefficient is larger than 0, smaller than 1, right? Okay. Okay, so I still have few minutes, right? Okay. Now let's talk about a general case, and we introduce a method. We call Boson diagram technique. We use this technique to find the time domain, to do the time domain analysis. Okay. Let's see, what is the general concept? So before we talk about this, let's simplify our analysis. Is we don't define the velocity and the absolute length, because we use one simple word. Because we use this, okay? Because this is the time to travel for one way, okay? The time to travel one way for the wave travel from here to here, the total length, how long it takes, that depends on the length divided by the velocity, right? So we always go this together. So we just use a simple one duration t. Okay, this one duration t, the one duration t that takes from one point to another point. Okay, from one point to another point. Now, let's see, when the wave start at the beginning, okay, at the beginning, the initial wave, with that, when the switch is on, okay, let's take a look of this example. What this example is, the intrinsic impedance is 60 ohms, the load is 120 ohms, the source is 40 ohms. Okay, then the one-way duration is 1 microsecond t. Okay, so at the initial time, one switch is on instantly. So what this can say, the voltage is the voltage divider. Okay, that's the voltage divider is the total voltage. Okay, the total voltage. Then I have impedance resistance 40, and then what it can say is 60, right? This is intrinsic impedance. Okay, this is 100 volt. Okay, then this is V plus at initial time. Okay, so voltage divided, this is this. Then the current that carries, is total resistance 40 plus 60 is 100 divided by voltage. So I had the previous note is not correct. Okay, this should be 100 divided by 100, not 60 by 60. So I found this error last night. But the result is the same. Okay, result is the same, but concept is not right. So because your total resistance is 40 plus 60, right? Okay, so this is total resistance and the current. Then we can find the voltage reflection coefficient at the load, okay, at the load on this side. So the reflection coefficient for voltage at the load, that is the load resistance minus intrinsic impedance 60 and plus, that is this, right? Okay, so that is 1/3. Then the voltage, the reflection coefficient at the source resistance become low. Intrinsic impedance, because you stand inside the transmission line, looking outside, right? When you look at the load, this is what you see. Okay, the load. When you look at located at the source, what you see is 40 ohm is your load, right? So this is how you find reflection coefficient, right? So we don't list the current reflection coefficient because that is the negative of voltage reflection coefficient. Now let's see what happened. You start from initial voltage 60. Okay, this is the duration time. This is before the time 1t. Okay, before you reach into this end. Okay, at any location, then you can see what you can have, right? At any location between the t, what you can measure is 60 volt, right? Is 60 volt. Then you hit on the wall, you reflect. Because reflection coefficient is 1/3, the reflection coefficient multiplied by the initial voltage is 20 volt, right? Okay, you return the 20 volt voltage. Okay, so this is V minus, this is V plus. Okay, then this voltage hit on this, and then you find reflection coefficient is minus 1/5. Okay, so 20 volts multiplied by minus 1/5 is this. So this voltage become, sorry, this is should be this become plus minus plus, right? Okay, and then you hit on the load and multiply by 1/3 reflection coefficient, reflect back again, right? And then every time you multiply by one reflection coefficient plus another reflection coefficient, another one, and so on. So this is what we have for voltage. And the B is the current. It's the same thing, but just initial current. You find initial current, you multiply by the current reflection coefficient, which is a negative voltage reflection coefficient, and so on. So the total voltage, okay, after a long time settle, okay, we call steady state, okay, or okay, the steady state. So that becomes stable. Right? So steady state, then that means I have initial one, I reflect and reflect again, and all this you add together. This is become what? Become a series, right? Then this easily you can find this is voltage. This is for the voltage I pick this, I pick this, I pick this, because all these add together become steady state in positive z direction. Okay. Then I can have a steady state. Oh, sorry. Steady state. Oh, no, this is steady state in minus that direction. I can add them up. This is equal to this. Okay. Similarly for current. Right? Then you can easily justify this relation. Okay, because the total wave travel in one direction, add them together, this is still traveling wave. If this is traveling wave, you can divide by intrinsic impedance to obtain the current. Okay. Also, in negative, the wave propagating in minus that direction, you obtain the same. Right. And if you add the steady state in two directions, that is the total voltage across. Okay, this is total voltage SS. Okay, no matter where you measure it, it's the same. Okay, no matter where you measure it, it's the same. So this is exactly, okay, exactly equal to if you connect the load directly to the source. You see, I didn't draw a transmission line. You see, why I draw transmission line? That means the size matters. But now I remove this, that means this is become ordinary electrical circuit. Okay, ordinary electrical circuit. So that means for steady state, the total voltage, stabilized total voltage, exactly equal to you connect the load directly to the source. Why is this? The reason is if you look at the transmission line, that means I have a load, I have a source, okay. You back and forth, you see, until a long time, you only have a DC, direct current applied to this transmission line. To DC, all the inductance is become short circuit. All the capacitance become open. Okay? So that's why this is become this. Okay? It becomes this. So that is for steady state. So for steady state, you really not need to worry how to find it. It's just this is high school stuff. But we need to understand why it happened is after you switch on for a long time. So this back and forth, then finally this become steady state. Steady state means you apply a DC voltage source to this LC circuit, you know what will happen. Okay, so let's stop here today. Okay. Okay, don't forget your attendance record.